today's topic. And all right, so on Monday, we introduced a bunch of numeric methods. Specifically, we were looking at root finding methods. And we said for root finding, we're looking for where the function crosses 0, okay? Or the x-axis, and we're just finding this. Now, I didn't mention this to the other class, but yeah, you could generalize that. And you can say, well, I just want to find where the function is equal to 100, or where the function is equal to -7, or something like that. And all you have to do is you just subtract that constant, right? So you just shift, if you want to find out where the function is equal to 100, just subtract 100 from the entire function. It shifts the function down, and now find the root of that new function. And that'll be where your function is equal to 100. Or you want to find out where the function is equal to -7, just shift it up 7 points. And where you find the root there, now you've got where the function is equal to -7. So that's straightforward enough. So on Monday, we looked at fixed point iteration for finding roots. We looked at Newton-Raphson method and its related cousin, the secant method. And we ran out of time before we got to bisection method. And so bisection method is a very simple method for numeric root finding. And the cool thing about bisection method is that it almost always works. It's going to work as long as there's one side that's negative and one side that's positive, okay? And it's a continuous function. So and the way it works is we bracket off a root, and we say, all right, here's an interval, and we know there has to be a root somewhere in this interval. And then all we do is we just shrink that bracket smaller and smaller and smaller in such a way where we're kind of guaranteed that a root is going to lie somewhere in the interval. And we half the size of the interval. So for bisection method to work, the rules are your function has to be continuous, okay? And you start off with some interval, and it's blocked by the camera there, but you've got x on the left-hand side, x on the right-hand side. And what we're going to say is that the function on the left-hand side and the function on the right-hand side, they have to have opposite values, okay? So f of x on the left has to be negative, and f of x on the right has to be positive, or f of x on the left has to be positive, and f of x on the right has to be negative. And a simple way to check to just see if they have opposite signs is you multiply f of x on the left and f of x on the right, and as long as that result is negative, then you know one is negative and one is positive, okay? So as long as they have opposite signs, then we know that a root has to exist between x on the left and x on the right. And we're going to just say there has to be at least one root, and then we are going to take that interval and shrink that interval, and we're going to keep shrinking that interval until that interval is less than some tolerance level epsilon, okay? So here is the entire algorithm written out here. We're going to start where you have x on the left, so x on the left has to be less than x on the right, and f of x on the left and f of x on the right have to have opposite signs. And if the difference between x on the left and x on the right is smaller than some tolerance level, then we'll go ahead and stop. And so that tolerance might be like 10 to the -7, 10 to the -8. So as long as if x on the left and x on the right are close enough together, like they're separated by 10 to the -8, we'll just go ahead and stop. Otherwise, if there is a difference between x on the left and x on the right, you find the midpoint. Okay, you find the midpoint. So you just do x on the left, x on the right, divide by 2. If by coincidence this midpoint is equal to 0, then we'll stop. Okay. Now that happens with a very, very, very low probability. So this probably you won't encounter this, but if you do happen to hit the midpoint, we'll go ahead and stop. If that midpoint does happen to equal 0. Okay. Otherwise, you're going to just check what is the sign x at the middle. And basically, you'll just compare, is f on the left-hand side, does it have the same sign or different signs than the midpoint? Okay? If x on the left-hand side and x at the midpoint have different signs, then we know the root has to be between x on the left and x at the midpoint if they have different signs. Okay? And so if x on the left and x at the midpoint have different signs, then your new interval is going to go from left to the midpoint. So the midpoint will become your new right-hand side of the interval. So you're going to say x at the midpoint becomes x on the right. Okay? And if they have the same sign, so if x on the left times f at x at the midpoint is greater than 0, then they have the same sign, then that means x at the midpoint and x at the right have to have opposite signs. Because we started off by saying x at the left and x at the right, f of x at the left and f of x at the right have opposite signs. So if the midpoint and the left-hand sides have the same sign, then the midpoint and the right have to have opposite sign. And so your interval will go from midpoint to the right. So you're going to take the midpoint and assign it as your new left-hand side. And then you just repeat over and over and over again. And at each step, your interval gets halved. Okay? At each step, your interval shrinks by a factor of 2. Okay? And this, and so the key here is that x on the left and x on the right always has a root somewhere in there because they have opposite signs. And this thing is guaranteed to converge as long as it's continuous and they started off with opposite signs. Okay, so here is an example. I've got some function, all right, and we're going to just use the same function we've been using, log of x minus e to the negative x. And we're going to try to find the root of this. So I'm going to just start off with some arbitrary value. X on the left is 1, x on the right is 2. And if I and we're going to just say we want to get a tolerance of 10 to the negative 8. So we're going to keep shrinking our thing until our interval is smaller than 10 to the negative 8. I evaluate f on the left. I evaluate f on the right. Okay? And so I have FL and FR. And do they have opposite signs? F on the left times f on the right is indeed less than 0. So f on the left and f on the right have opposite signs. That is true. Okay? So to run this algorithm, this is all I'm doing. I'm just running the code for this. I'm going to just specify start off iterations equals 0 to see how many iterations it took. And we're going to just run this as long as x on the right minus x on the left is greater than my tolerance. So as long as that difference is greater than 10 to the negative 8, we're going to keep running. We're going to first calculate our midpoint. X on the left plus x on the right divided by 2. And I'm going to calculate the function at the midpoint, f at m. Okay, f at the midpoint. And I've already calculated f on the left and f on the right. These exist in the global environment. And, well, I'll just pause here and I'll say, is f at the midpoint equal to 0, right? And this is approximately equal. All dot equal is approximately equal. Is it within a machine epsilon of 0? And if it is, then we'll break. And if it's not, we'll continue. Now I have to do this identical, I have to do this identical business because unfortunately all equal returns true if it's true, but it doesn't return false when it's not. It returns like a character string that says something like mean relative error 10 to the negative 7 or something like that, which is that's not helpful for us. So in order to kind of turn it into a true false, we're going to say, is it identical to true? And if it is, it's true. And if it's not identical to true, it's false. Okay? Okay, so, and this is pretty much most of the bulk of the bisection method. We're going to say if f on the left and f on the midpoint have opposite sides, then the midpoint becomes the new right-hand side. If that's not the case, then the midpoint becomes the new left-hand side. And then we repeat. Okay, add 1 to the number of iterations. We repeat that, and then the loop continues running. And then at the end, our answer is going to be the midpoint of x on the left and x on the right. That will be the answer. So the midpoint is 1.3098, which maybe is a familiar answer because that's what we saw several times on Monday when we were looking for roots of this function and we kept getting 1.3098. The number of iterations it took to get to our answer was 24, okay? Just to kind of illustrate what this looks like as far as pictures go, and it's not necessary to draw this picture for the algorithm to run, but just so you guys can see how it works, this is what the function looks like from 1 to 2, okay? And so we have a root somewhere around here at 1.3098, but I start off from 1 to 2. 2 is positive, f at 1 is negative. I calculate the midpoint. Okay, the midpoint at 1 point is 1.5. F at 1.5 is positive. So I'm going to throw away the right-hand side because this is positive. Positive, we want to make sure we have opposite sides. Okay, at the next iteration, I calculate the midpoint of 1 and 1.5, which is 1.25. F at 1.25 is negative, and so we're going to throw away this side. We want to make sure we're bracketing the root. We need to have one side be negative and one side be positive, so we're going to throw away this side. Okay, now I'm going to find the midpoint here, which is going to be like 1.375. Okay, and when I do that, I get this. This value is positive. We're going to throw away this side. Okay, now I'm going to find the midpoint here. The midpoint here is right here. Okay, and it looks like it's very close to 0, but it is very close to 0, but it's not within the tolerance. So we're going to keep going, and we're going to throw away this side. Okay, so this side is very close to 0, but and this side is negative, so we're going to throw away that side. We're going to keep this side over here. I half this, and I throw that away. I half that further, and I throw that away. And we just keep going and going. We just keep splitting this interval smaller and smaller and smaller, and we can just imagine this continuing, and bisection method will eventually get an interval that's small enough. After 24 iterations, the difference between the left and the right will be on the order of 10 to the negative 8, and that will be where we've decided our root is. Okay, is that all right? We run into issues. I'll try to get this in the video here, but it's a little. So this is kind of where. So if you have, say, a function that looks like this, and let's say this is x on the left, and this is x on the right. Okay, so x on the left is negative, x on the right is positive, and we say, okay, there's got to be a root somewhere in here. Okay, and so you say that here's the midpoint, x at the midpoint, and we're going to calculate this thing. And so as far as the algorithm is concerned, it's going to say the root has to be between here and here. Okay, and it's not going to recognize that there's actually two roots between here and here, because as far as this goes, x at the midpoint is positive, x on the right is positive, and it's going to say, well, we're not guaranteed to have a root in here. Okay, there is, and you would only know this if you graphed it. Okay, but we're going to just say, okay, well, there has to be a root here, and then we're going to split this, and this is positive, and just kind of keep going, and this is positive, and eventually we'll get there. Okay, so that's an issue. Now, hopefully you can start off with maybe some kind of interval where if you have multiple roots, you can kind of at least isolate them a little bit. Just simple. When we looked at Newton-Raphson method on Monday, we said Newton-Raphson method is not guaranteed to converge, and that's true. Okay, it's not guaranteed to converge. But we said, if your Newton-Raphson method, it's heavily dependent on your starting location. And we said if the function is well behaved and you're starting close to the root, then you'll converge to the root. And so we said, well, that's great. So one thing you can do is you can start off with bisection method and use bisection method to get you to an interval that's fairly close to the actual, close to a root. and then you can switch over to Newton-Raphson method, right? So maybe you start off with a big interval, use bisection method, maybe that gets you to within, 1/10, 0.1 of the root. And hopefully within that interval, it's well behaved and close enough, and you can switch over to Newton-Raphson, which converges quite a bit more quickly. Let me see. Let me give you your first view quiz answer for today. Today's answer is, what is it? C. C is your first view quiz answer. C as in cat. C as in cat is your first view quiz answer. Okay, so there is this concept of order of convergence. And basically, we can ask, what is the order of convergence of some method? And the idea is, okay, let's say you have the approximation, okay, is for, after the nth iteration is going to be x sub n, okay? So if the actual root is a, and your approximation after the nth iteration is x sub n, we're going to say the error is e sub n. And this is going to be kind of your nth the order of convergence. We're going to say, okay, the value of e sub n at the next iteration, e sub n plus 1, can we express it in terms of the error at the previous iteration, e sub n? And if you have some value of p here, you take this and you raise it to some value p. Larger values of p correspond to faster order of convergence. Higher orders of convergence mean it's going to converge to that root even faster. Okay, we're going to kind of skip all of the derivations and the math. This is just kind of a high-level conceptual overview of this concept of order of convergence. So if you think about bisection method, the interval, the amount of error you're going to have, shrinks by a factor of 2, right? Every single time you're cutting your interval in half, okay? And so it's shrinking by a factor of 2. And so the next value, okay, the next level, the size of the next error is going to be your current error divided by 2. And so this is what we call linear convergence. We're not taking our current error and raising it to any kind of power. We're just taking our current error and dividing it by 2. Okay, so that's linear convergence, and it's pretty good. Okay, the amount of error is shrinking by a factor of 2 every single time. Newton-Raphson method, however, has a much faster order of convergence. It has quadratic convergence, and again, I'm going to skip the math here, and you'll just have to take my word for it, or you can kind of explore some of these things that I've linked to. But it's going to, the amount of error you have at the next iteration, that amount of error is much, much smaller, okay? We're going to say it's got quadratic convergence. And so we like Newton-Raphson method a lot. It's just, as we saw on Monday, there's all sorts of situations where it doesn't work, okay? Secant method is kind of like Newton-Raphson method, except instead of drawing the tangent line, it's drawing a secant line, okay? And again, skipping all of the math, you can do the math and derive it, and it turns out, just kind of like by magic, not even, because of math, right? Some interesting stuff happens. It has a convergence rate of 1.618, which is the golden ratio, which shows up in all sorts of places, Fibonacci sequences and stuff. But we get a convergence on the order of 1.618. Okay, so anyway, all to say, bisection method has kind of the slowest convergence, but this is the one that's guaranteed to work as long as you have a continuous function and your interval starts off with opposite signs, whereas Newton-Raphson has a better orders of convergence, but isn't guaranteed to converge. So these are some of the issues that we run into. Let's talk about this topic of derivative approximation. Okay, so with derivative approximation, going back to Newton-Raphson method, we said the way Newton-Raphson method works is that the next value at x at time n plus 1, your next approximation for the root is going to be your current value minus f of x divided by f prime of x. Okay? You take your current approximation, you plug that into f of x, and divide by f prime of x. That's going to kind of give you the run, and you subtract it off from the current value. And that's going to be your next thing. Now, what this requires us to find the derivative of the function. And so when we were dealing with our problem here, we said our function is log of x minus e to the negative x. We said, okay, what's the derivative of this? Derivative of log x is 1 over x. Derivative of e to the negative x is e to the negative x. Chain rule turns it into a plus e to the negative x. And we wrote functions. We said f is log x minus e to the negative x. F prime is 1 over x plus e to the negative x. And we can say, all right, at 5, this is our function. And the derivative is 0.2067379. And so we can just plug in 5 into our function f prime here and get our derivative. And this is the slope of the tangent line. And that's it, okay? Slope of our tangent line. That's great. So that was fine. We had the derivative. We have f of x. We were able to find the derivative of f of x. Sometimes we're in a situation where finding the derivative can be a headache, or we don't want to. Okay, so what do we do in this situation? What if we didn't want to figure out the derivative of a function? Okay. Well, we can approximate it. And the way we're going to approximate it is we're going to use the definition of the derivative. So back when you took calculus, the definition of a derivative is the derivative at point A is going to be f of a, right? And then you also calculate the function at a plus h. You add some small increment h, or delta, or whatever you wanted to call it. We're going to do f of a plus h. And we say, how much did the function change, right? If here's a and here's a plus h, how much did the function change from here to here? And we say, this is how much it changed. F of a plus h minus f of a. That's how much the function changed. And we're going to divide that by the size of h. And we say, we're going to take this to the limit as h goes to 0. Okay, what is this thing? And so all we're going to do here is we're going to just take this and just say, you know what? We're not going to take it where h goes to 0, but we'll approximate it with h being some small value, like 10 to the negative 6 or something like that. Okay, so what if I plug in a small h, so suitably small value of h? This will give me an approximation here. Right. So here we're going to find an approximation for f prime for this function log of x minus e to the negative x. And I'm going to use 10 to the negative 6 as my value h. Okay, so I've got, so I'm going to plug in x here. F of x is going to be log of x minus e to the negative x. And then I'm going to say f of x plus h is going to be log of x plus h minus e to the negative x plus h. I take the difference between f of x and h minus f of x. I take that difference, I divide by h, and we're going to return that, okay? And so my approximation is 0.2067379236669. Okay, here I said print out 12 decimal places of precision here. Let's compare that to f prime, the true, quote-unquote, true value. So I created this function f prime as 1 over x plus e to the negative x. I said, what is that value? So the quote-unquote true value is this, 0.20673794699. And so we can see that these two numbers are very close to each other. They are accurate. They have the same values up to 8 decimal places. 0.2067379, or I guess 7 decimal places. Okay, 7 places after the decimal, they have the same, and at the 8th position, they're a little bit different. This one's a 2. This one's, the true value is 46. Okay, so it's a pretty good approximation, I think. The way I calculated this was I calculated the value of the function at 5, and I've calculated the value of the function at 5 plus 10 to the negative 6. What if instead I calculated the value of the function at 5 and the value of the function at 5 minus 10 to the minus 6, okay? So what if my h is negative? Okay, how is that going to compare? So same function, except here the h, instead of being plus 10 to the negative 6, I'm doing 10 to the negative 10 to the negative 6. Okay, and so the true value, f prime, is 0.20673794699. If I use the negative approximation, it's 206,737, and then the value where it differs, instead of 4699, I get 70299. And if I take the right-hand side approximation, then my last 5 digits go 23699. So here I got 0.23699 versus 0.70299, and over here I got 0.46999. Okay, and so to show you what's going on, okay, because of the curvature of the function, which so this is a very exaggerated picture. Okay? So if this is my value at 5, okay, your tangent line looks something like that. Okay, this is our tangent line. This is what the function looks like. Now, if I take this, if this is x, and over here I come over here to this is x plus h. So this is, again, very, very, very exaggerated. And I say, what is my approximate slope here, going from x to x plus h? We can see this slope, this is less steep, right? And if I come over here, and I have x minus h, and I say, what's the slope here? Okay, this one is a little bit more steep. And this value is the true slope, right? If you can see what's happening there. So I've illustrated that on this slide. This is, again, extremely exaggerated. Okay, here I have h, instead of being plus 10 to the negative 6, I have it being plus 1 and h negative 1. So I'm drawing an approximate slope at h plus 1 and h negative 1. And we can see that the right-hand side approximation is less steep. The left-hand side approximation is too steep. So maybe I can get a good approximation by averaging the right-hand side and left-hand side approximation. Okay, and so that's what I have here. A balanced approximation for f prime is I'm going to take x plus h and f of x minus h. So we're going to do log of x plus h minus e to the negative x plus h, log of x minus h minus e to the negative x minus h. We're going to take the difference between these two things, and we're going to divide by 2h instead. Right? And so this will give us kind of an approximation. So here the right-hand side is less steep, the left-hand side is more steep. That's because this curve at this location is concave down. If we had a function that was concave up, we would have kind of the opposite problem. We would get the right-hand side is more steep and the left-hand side is less steep. It doesn't matter. We've got the balanced approximation looking like this. And so if I use the balanced approximation versus the quote-unquote true value, we can see this is accurate up to, I think, 10 places of precision, or what is it? 0.2067379466984, and the true value is 0.20673794669, and the last two, 99. So we're accurate up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places after the decimal. Okay, so that's pretty good. Okay, that's pretty good. And we can generalize this. We don't have to keep using log of x minus e to the negative x, we can just generalize it to just any function. Any function. Okay? So here I'm, remember in R, functions themselves are objects and we can pass them as arguments. So here I'm going to just say, what's the derivative of some function ftn? And we're going to say, what's the derivative at x? I'm going to do, on the left-hand side, we're going to find the value of x minus h. The right hand will be x plus h. We're going to evaluate the function on the right minus the value of the function on the left and divide that by 2h. And this will give me an approximation of the function here. So, so this will work here. Let me give you your second view quiz answer. Today's second view quiz answer is B. B as in bear. B as in bear is your second view quiz answer. All right. And so because of this, we no longer have to actually analytically calculate the derivative. We can just kind of estimate the derivative by calculating the value of the function at these two locations, take the difference between them, and divide by 2h. Okay? And that will give us kind of a balanced derivative by taking kind of the right-hand side and the left-hand side and taking it. Basically, effectively what we're doing is I'm doing x plus h, and we're finding the slope here, and the idea is that this is going to be kind of parallel, maybe a little bit off, but close to being parallel to the true tangent line there. Okay, so how does this work? So when we here is the function f, and here's how I run it. I run f derivative on f. I plug in 5, and I get this is my approximation. What if I tried a different function? So over here, I just made a new function. The function is x squared. And so we know the derivative of x squared is just 2x, okay? And we can see how this works. So I can say, give me the derivative of this function f2, which is x squared, at 5. And it comes back and it says, oh, that number's 10. And we'll go, oh, great, it's working, okay? What's the function? Right, 2x is 10. And we can see, all right, if I do digits equals 12, we can see, oh, it's a little bit off, right? The true derivative is 10, and here we're getting 10.00000000014. So we're off by a little bit. At the 11th decimal place, we're off by a little bit, okay? And we can see, how do our approximations differ with different size h's? Okay, so what we're doing is we're approximating it by just adding an h, subtracting off an h, and seeing how much did the function change. So what if my h is 10 to the negative 5, 10 to the negative 6, negative 7, 10 to the negative 8? And at first glance, we might think, well, because the definition of the derivative is as h goes to 0, we might think, let's use the smallest possible h that we can use. But if you look closely, at 10 to the negative, if h is 10 to the negative 6, we're accurate to, I think, 1, 2, 3, 4, 5, 6, 7, 8 decimal places, and the 9th spot is off by 1. If I use 10 to the negative 7, I'm accurate up to 1, 2, 3, 4, 5, 6, 7 decimal places, and I'm off by 3, or 2, 8. If I go to 10 to the negative 8, I'm accurate up to 7 decimal places, and I'm off by a little bit more, by like 0.6. And as my h's get smaller, 10 to the negative 10, negative 12, negative 14, at 10 to the negative 15, my derivative approximation is 8.8, which is not that close to 10. And at 10 to the negative 16, my derivative approximation is 0, okay? So shrinking h actually doesn't improve performance. What's going on here? Why are we encountering this problem? What do you guys think? So if we were dealing with real numbers, yes, shrinking h as h goes to 0 would give us the derivative, okay? Would give us better answers for the derivative. What we're running into is problems of the limitations of floating point arithmetic. Okay, so floating point arithmetic, when you add just a tiny value to something, the computer has a hard time kind of detecting some of these changes. It's like you have 52 bits in the mantissa, and that corresponds to around 16 places of accuracy. And so when you're going to do something like 5 plus 10 to the negative 16, it actually, I think the computer has a hard time distinguishing between 5 and 5 plus 10 to the negative 16 and 5 minus 10 to the negative 16. And I think, in fact, the computer sees these things as equal, right? So when you say, what's the value of the function at 5 plus 10 to the negative 16, and what's the value of the function at 5 minus 10 to the negative 16, it might say, oh, you're plugging in the same value into the function, and it says there's no difference. And so we're getting a difference of 0, a derivative of 0. And when we're adding 10 to the negative 15, it's not actually able to represent 5 plus 10 to the negative 15. Its approximation is something kind of a bit off. And so when it does its calculations, it's getting something quite a bit off. And so we have to keep in mind that the computer has floating point limitations. And so just shrinking h to be as small as you can possibly make it isn't actually going to give you more accurate results. And depending on what number you're using, so here I'm doing 5. So for 5, 10 to the negative 6 is a decent number to add or subtract. But what if I want to find the derivative at x equals to 1,000,000? Okay, if x is equal to 1,000,000, then I probably have to add a much bigger number, right? Because at 1,000,000, the limitations of floating point numbers probably can only represent up to something like 10 to the negative 2 or 3 or something like that, in comparison. I mean, not the limitations is 2 or 3, but just more accurately, something on that order. So you have to keep in mind some of these things. We're not dealing with real numbers. We're dealing with floating point numbers, which has a limited number of kind of places of accuracy that we can represent. Okay, let's talk about our last topic here. How many view quiz answers have I given you? 2. Okay, I'll hold out on the third one. So now we can talk about numeric optimization. Okay, and we'll cover a few numeric optimization methods, but for now we'll look at derivative-based numeric optimization. So far we've covered a bunch of kind of root finding methods. We talked about approximating a derivative. And let's say we want to find the local min or local max of a function. Okay, so finding local mins and local maxes is known as optimization. This is kind of the job of optimization. We want to find out where is a function maximized, where is a function minimized. That's often what we're trying to do, right? We try to minimize the cost of something. At what speed should you drive your car so you're using the least amount of gas or something like that, right? We're trying to optimize our thing. And a lot of our functions are written for finding the local minimum of some function f. And if you wanted to use the same thing to find the local maximum, all you have to do is multiply f by -1, and you find the minimum f times -1, and that'll be the maximum, local max. Global mins and global maxes are really hard, so we're not even going to try to generalize some kind of thing that's going to work for global mins and global maxes. Okay, well, this is how derivative-based numeric optimization is going to work. We're going to say find the derivative of some function f, right? If we want to find the local mins or local maxes of a function f, first find the derivative, f prime. Find the derivative of f. And then figure out where your derivative is equal to 0. And we can apply a root finding method. So we've covered several root finding methods, Newton-Raphson, fixed point, secant method, bisection method. You apply one of those methods for finding a root. Find the roots of f prime, and if you find the roots of f prime, those will be your critical points, and you can evaluate that. So to figure out where you have local mins and local maxes. because we learned that in calculus, right? When your derivative is equal to 0, that's got to correspond to either a local min, a local max, or maybe a saddle point. And that's all we're going to do, is we're just going to find the derivative, set the derivative equal to 0, use a root finding method to figure that out, figure out our critical points and evaluate those. So if we wanted to, say, apply this strategy for Newton-Raphson method, this is what it would end up looking like, okay? So all this would basically do is find the roots of f prime using Newton-Raphson method. So instead of finding the roots of f, we're going to find the roots of f prime. We find the roots of f prime, that'll give us locations of possible local mins and local maxes. And just like Newton-Raphson method, it may or may not converge to the roots, but this is how it's going to do. So our next iteration at x at time n plus 1 is going to be x at time n minus, and instead of doing f divided by f prime of x, it's going to be f prime of x divided by f double prime of x. Okay, and this will help us find, or this will find the roots of f prime, and when you find the roots of f prime, that should correspond to either local mins or local maxes of f. So the rules here is that f needs to be twice differentiable, and now f prime cannot be 0 for any of the xn's that you check. F double prime can be 0 as long as it's not within the sequence of xn locations that you get that are get evaluated here. All right, so here's just a very simple example. Here's f 0.25x to the fourth minus 0.5x squared. Here's your first derivative. First derivative of this is x cubed minus x. Second derivative is 3x squared minus 1. Okay, so we've done this analytically, and we can find the roots just using this. So I'm going to just kind of code this up. This is what the function looks like. We can see we have a local min at -1 and 1, and the local max at 0. And like Newton-Raphson method, it's heavily dependent on your starting location. So here I'm going to start at 2.1. F prime is x cubed minus x. F double prime is 3x squared minus 1. And we're going to do take x old minus f prime of x old divided by f double prime of x old. That's going to be our x new. That goes into our while loop. Starting at 2.1, I run this, and it says your root is at 1. And that's going to be where the derivative is equal to 0. And indeed, that corresponds to a local minimum. If I start off at somewhere else, say 0.9, it's going to take me to 1. It takes me to 1.0000308, so pretty much 1. Okay, and again, we get that. If I start off at 0.1, then it takes me somewhere very close to 0, 10 to the negative 24. If I start at, say, negative 10, it converges to negative 1. So it ends up finding all of these roots, or not roots, it finds the roots of the derivative, and where the derivative is equal to 0, that's going to correspond to a local min or local max. Now here, for this Newton-Raphson method, I had to find f prime and f double prime. But you technically don't need to find those directly. You can use our derivative approximation. All right, so if you wanted to use a derivative approximation, you can use this, because all we're doing is we're just plugging in, and the computer, when we say let's find f prime and find f double prime, the computer doesn't know that this was the result of an analytic approach or an approximation approach. It's just taking numbers and it's just multiplying or dividing them. It doesn't care. So if you didn't actually bother solving for these first and second derivatives, you can just use our derivative approximation method, and you'll get approximate derivatives, and this will give you still an approximate root. Okay, maybe it won't be as accurate. It might be off by even a larger factor or something, but it'll still get you pretty close. And again, that's all we're aiming for. We're not trying to get mathematically precise answers. We're just trying to get approximate answers. And that's what we're doing here. Okay, let me go ahead and give you your last view quiz answer. Today's last view quiz answer is A. A as in apple. And we'll end there. Okay, so that'll be it. This is just kind of some more approximation methods, numeric methods, and we'll take a look at some more of these numeric methods. And other than that, we'll see you all on Friday. So have a good rest of your day. And homework 5 has been posted. Homework 5 is now starting to deal with numeric methods. And so I know you're still wrapping up homework 4, but homework 5 is online now, and you can take a look at that. Okay, see you on Friday.